Okay, hi everybody. Here we go. We actually have 5 units to get through today. Sounds like a lot, but we're going to skip one because it's not on the exam. And a couple of them are pretty short, so I think we can do it. The timer has started. First thing I'm going to ask you to do, and I am actually going to give you a minute to do this, is see if you can figure out each of these. See what you can remember. Believe it or not, practicing using your memory is actually a good way to improve your memory. So this is actually useful to sit and think for a minute on what each of these is. But we won't wait too long. If you want a little bit longer, you can pause the video. Okay, this is actually pretty boring because I'm just staring at the screen, so I'm going to get started. So sine, that one hopefully is easy. That's just cosine u, but don't forget times u prime. And cosine of u is, tricky, negative sine u times u prime. So that's times the derivative of the angle, the thing that you're taking the sine of. And then for these next 4, you're actually only really have to remember one, sort of, or 1.5 maybe, let's call it. And that's this one, which is secant squared u times u prime. Okay? And because then the other one is just the opposite of that, negative cosecant squared u times u prime. And then this one is just the same thing, secant u times tan u, which is just this thing and this thing times u prime. And this one is the same thing, cosecant u times cotangent u times u prime. So once you kind of get one of them, everything else falls into place. Okay, so hopefully you remember that. You definitely want to remember that in case any of those pop up. Definitely, I would think that like one of them might pop up on the test, on the final exam, okay? Here we go. Find all critical values and the intervals of increase and decrease for the function below on the given interval. Now, this is one of those ones that people tend to be actually very good at, but sometimes don't do as well because they don't really understand what this is asking us to do. So, we talked about this yesterday, but what is this actually asking us to do? Does anybody know? First derivative chart. That's it. Why don't we just ask straightforward? Do a first derivative chart for it? Because you should know that what the first derivative chart accomplishes. We should know to find the intervals of increase and decrease what we have to do. Okay, so it is important. So, critical values occur when y prime equals 0 or does not exist. This doesn't have any asymptotes. It's trig function. So let's go ahead and find the first derivative. So the derivative of sine of 2x is cosine of the same angle times the derivative of the angle. So the derivative of the angle 2x is 2. So this is 2 cos 2x. The angle stays the same times the derivative of the angle minus 2 times the derivative of sine x, which is 2 cos x. Okay, y prime exists for all x. So we're good with that. So where does y prime equal 0? This is where it gets tricky. 2 cos 2x minus 2 cos x. Well, first of all, I'm going to divide out a 2 and just be done with that. And I could write that as a line, or I could do that in my head. Then I have to figure out what to do. And this is where, you know, there's a lot of identity stuff going on. And one thing that I notice is I'm not going to be able to resolve this when I have different angles. So cos 2x and cos x is not going to work. So I have to think about the identities for cos 2x. And there are 3 identities for cos 2x. Okay? And the one that I want is the one that has cos x in it. So I'm going to use that one. So I'm going to divide out the 2's. This is like 0 over 2 equals. So one of the identities for cos 2x is 2 cos squared x minus 1 minus cos x. Remember, I divided out the 2. And then I get 2 cos, whoops, that 2's in the wrong place. That's what I want. Thank you very much. And so I get 2 cos squared x minus 2 minus cos x equals 0. Wait a minute. So this gives me the so now I have 2 cos squared x minus cos x minus 1. Okay, good. Equals 0. And this is something that I can factor and actually solve. So this is like 2x squared minus x minus 1. So it factors to 2 cos x plus 1 and cos x minus 1 equals 0. Which means each of those 2 brackets equals 0, which means cos x equals negative 1/2 and cos x equals 1. If cos x is 1, that's an easy one. I'm going to use the graph, and x is either 0 or 2 pi. And that's worthwhile going back and thinking about our interval, our domain that we're actually graphing this on, but it includes both those points. They're the ends of that domain, so that's fine. And negative 1/2 is a special angle value. So x related for 1/2 is pi by 3. And that makes, if it's negative, that makes x 2 pi by 3 and 4 pi by 3. Okay, so I've got all my critical values, but I have to determine the intervals of increase and decrease. So I go ahead and start building my chart. So I start at 0, and then I go from 0 is less than x is less than 2 pi by 3, 2 pi by 3 is less than x is less than 4 pi by 3, is less than x is less than 2 pi, and then 2 pi. Okay, and I've got y prime and then y. So at 0, that's a critical value. So y prime is 0. And I'm going to punch this in my calculator. I'm going to put it in my calculator. I'm going to put it in the memory function to make this easy. And I'm going to pick a value between 0 and 2 pi by 3. 1 might be a nice value to use in there. I think 1 would work. And I get negative. Or I can use something just above 0 for that matter. It's pretty easy once you use the memory function to put anything in. I can put something just a little bit bigger than 0. 0.5, 0.1, whatever you want. And that works out to negative. 2 pi by 3, again, was one of the critical values, so that's 0. And then in the next one, I pick pi. 2 pi by 3, 3 pi by 3, 4 pi by 3. 3 pi by 3 is pi, so I pick pi. 4 pi by 3 is 0. 4 pi by 3 to 2 pi. 2 pi is a little bit more than 6, so I think I would pick 6 in here. And that works out to negative, and then the last one is 0. So if it's negative, I know that if the first derivative is negative, I know it's decreasing. If it's positive, I know it's increasing. If it's negative, I know it's decreasing. If it's decreasing and then 0 and then increasing, that looks to me like a local minimum. Okay. If it's increasing, then 0, then decreasing, that looks like a local maximum. And because I don't know before what happens, I don't actually know about these two. I just know that it's a horizontal tangent line. It's a horizontal tangent line. And we know a lot about these kinds of curves, so we do have a sense of what would happen. You could guess, but we don't know for sure if it's a twist or if it's actually a local maximum. We just know it's a critical value, and that's fine. If it's at the end of the interval, you just say, we're not sure. Okay, and it just said critical values. It didn't say critical points, so we're done. Find dy by dx. This is an implicit differentiation question. Derivative of tan is secant squared. So this is secant squared of the angle times the derivative of the angle. So the derivative of 4y is 4. And then remember the implicit part, dy by dx. Minus. And this is, I'm choosing to put the minus outside. You don't have to, but that's what I'm going to do. So I'm going to put the minus outside. And this is a product rule. This is one of those ones that can be sneaky. Some people don't see it, but x times y is a product rule. So it's the derivative of the first thing, which is 3x. So the derivative of that is 3 times the second thing, which is y. So it's 3y plus the first thing times the derivative of the second thing. And the derivative of y is just dy by dx. If you ever get stuck on that, just think when I have a function that says y equals something, and I take the derivative, I get dy by dx equals. So what's the derivative of y? It's dy by dx. That's it, right? And what's the derivative of 1? A derivative of a constant is 0. So I put 0. So now I have to isolate the dy by dx and solve for that. That's all. Okay? So I'm going to expand that bracket, and I get 4 secant squared 4y dy by dx minus 3x dy by dx. And I'll move the negative 3y over, equals 3y. Why not? Save a step. Common factor, the dy by dx out. And then, I'm going to common factor, and I'm going to divide by that anyway, so I can do that all together. 4 secant squared of 4y minus 3x. And there we go. Implicit differentiation. Remember I said any of those implicit differentiation questions could pop up in any of those functions. It could be a trig function, it could be a logarithmic function, it could be any of those. All right, let's see what's next. So we're already done with trigonometry. Logarithms and exponents. We're going to do the same thing here, where we are going to, and if you could take a minute to do this, that'd be great. We have 4 options here. So E is our special number, and B is just any number. Okay, so take a minute and try to fill those in. I don't really need that much space. All right, let's start filling these in. This one's about as easy as it gets, right? E to the x is e to the x times the derivative of the exponent. And the next one's pretty easy too. It's just 1 over the argument of the ln. Okay, so what about the other ones? The other ones require a bit more work. So what is the thing that we have to add to the other ones to make them work out? So a lot of it is the same. It's going to be b to the u times u prime, but then I also multiply by the ln of u. Sorry, not ln of u, ln of b. Whatever the base is. So that's a constant. It's not u because that would include an x. It's a constant. Okay? And that's why, if you remember all the way back then, that's why it's useful to do all of our derivatives with a base of e. Okay, and the next one's similar. It's 1 over u times the ln of b, and then all of that times u prime. All right, let's get into this. Okay, so this says differentiate first line only. No need to simplify. So we notice this first one is product rule because I've got this thing times this thing. So we got to use the product rule. The derivative of the first thing. Now the derivative of the exponential function is itself. So I've got e to the negative 3x squared times the derivative that is in the exponent. So times the derivative of the exponent, which is negative 6x, plus the first thing times the derivative. Oh, sorry, missed that. Missed a whole part of this. Times the second thing. Now plus the first thing, which is e to the negative 3x squared, times the derivative of the second thing, which is 1 over the argument of the ln times the derivative of what's inside. And so if we had to simplify that, that often simplifies very nicely. And then plus the second part. There's a whole second part here. So plus And again, this is the exponential function, so e to the cos of x minus 6 times the derivative of what's inside, and the derivative of cos of x minus 6 is negative sine of x minus 6. And if x minus 6 had a derivative that was other than 1, I'd be multiplying by that too. So I multiply by the derivative of the angle of the sine function, but that's just 1, so it doesn't do anything. So that one's done. No need to simplify. There's lots of little simplifications that could happen and a little bit of factoring and that sort of thing, but I don't need to do that in this case. Okay, and now I have a quotient rule. This is a pretty big one as well. So derivative of the top, which is the derivative of the exponent, so 8x is the derivative of the exponent, 4x squared minus 1, times 3 to the 4x squared minus 1 times the ln of the base 3, because that when it's base e, I don't have to do that part, but when the base is anything else, I have to remember that and include that. Times the bottom. Minus the derivative of the bottom times the top. So the derivative of the bottom is the x cubed times the ln of 4, because it's log of base 4, and then all of that times the derivative of the argument, so that's 3x squared. You can do that separately. You could do 1 over and then times 3x squared, or you can collect it together in one fraction, and all of that times the top, so that's 3 to the 4x squared minus 1. And then plus just that last thing. So this is a little bit of a strange one, but it's x to the pi. Sometimes these things throw people off, but pi is a number, so this is like x squared. So this would be, sorry, not times, plus pi x to the pi minus 1. And that might not be something we've quite seen yet, but that would be how you would do something like that. So if it's not an integer, you would still do it the same way like we do with just monomials. And I forgot one part of that first one. This should all be over the bottom squared. So that was a little out of order. Okay, so this whole part here came from the quotient rule of this. So that's why it's over the bottom squared. And then I have the second part over there on the side. And I think that's done. First line only, so that part's done. And I believe this is an example of logarithmic differentiation, because if I look at it, I've got an x in the base and an x in the exponent. So we know that the only way that are our best way to find the derivative of a function like this is logarithmic differentiation. And the first part of that is take the ln of both sides. So this is the ln of y equals the ln of this whole thing. But the whole point is with that, I can take the exponent out front. So this is x over 2 times the ln of 2x minus 5. So I use one of our logarithm laws to pull the exponent out front. And this is what allows me to take the derivative of something that has an x in the base and an x in the exponent. Okay, then I take the derivative of the entire thing. So this is the derivative of ln of y is 1 over y dy by dx. And the second part, again, is product rule. So the derivative of the first thing, this is 1/2 times x, so it's 1/2 times the second thing, which is the ln of 2x minus 5, plus x over 2 times the derivative of the second thing, which is 2x minus 5, and then the derivative of the argument, which is 2. Okay, and then this one I do have to simplify because I've got to bring the y over and do a couple more steps for a question like this. And I got dy by dx equals y times the ln of 2x minus 5 over 2 plus x over 2x minus 5. And does anybody remember what the last step of the rule for these is? We want an expression in terms of x, not in terms of y and x. In this case, it's fairly easy to do. So dy by dx equals, I sub in for y, which is what we were given here, so that I have an expression in terms of x. 2x minus 5 to the x over 2 times this whole big mess. And now I'm done. Related rates, hey, we get to skip this. We're not going to bother with this. You can try those questions if you like, and we can talk about them, but we don't need to worry about it for the exam. So let's finish up these last couple of units on vectors. All right, so f to b is from here to here. Oh, and so I'm going to just do this. Vector u is ab, so here's vector u in that direction. And vector v is a to f, so this is vector v here. And that might help me. So if I do, so I'm going to break this up into f a plus a b. And fa is the negative of af. You don't have to show this step. And af is v, so that's negative v plus u. Okay, that's fb. A to d. Now, probably people's initial idea would be to go this way for some reason. That seems to be what people like to do. But it's better to actually go from A to F, F to C, and then C to D, because A to F and C to D are the same. And we know FC because we know AB, and FC is 2AB. Okay, so I'm going to move that one, and I'm going to bring this one over here. And I get this equals AF plus FC plus CD. AF is V. FC is 2AB, which AB is U, so that's 2U. And CD is the same as AF, so that's plus V. And then we should simplify this, so that's 2V plus 2U. And that one's done. And the last one, C, is FD. This one's kind of similar, actually, I think, in some ways. Okay, so for FD, I want to just do F to C and then C to D. So F to C plus C to D. And FC again, we saw this already, is 2U. And CD is V. Very similar to the other one. Okay, hopefully that's pretty straightforward. Let's see some more stuff again. This is pretty straightforward. A lot of this is just notation. So 3 times vector u, I'm just going to do this right away. So that's 3 times negative 1, 3 times 2, and 3 times 5. Minus 4, and I'll do v minus w. So 3 minus negative 7 is 10. 4 minus 0 is 4. Negative 6 minus 1 is negative 7. Okay, multiply by 4. I'll still subtract it and just multiply through by 4. So 40, 16, negative 28. Negative 3 minus 40 is negative 43. 6 minus 16 is negative 10. And 15 minus negative 28 is 15 plus 28, which is 43. Okay, so it's really just bad math stuff, adding scalar multiplication of vectors. This one's almost the same, but we're going to take the magnitude at the end. So u plus 2v is u plus 2v, so that's 6, 8, negative 12. Multiplying each of those components by 2, add those together. 5, 10, negative 7. And then the last trick is, if you remember, how to take the, how to find the magnitude of that. And that's just similar to Pythagorean theorem. I just square everything. And I end up with this root 174. Done. Okay. A unit vector in the opposite direction of uv. Oh, of u, sorry. I'm getting these two mixed up. They're kind of clumped together. Bad formatting again there. A unit vector in the opposite direction of u. So that would be like negative u, first of all, is the opposite direction. So that would be positive 1 and negative 2 and negative 5, just taking the negative of everything. And then I want to find the magnitude of u. So again, that's a square root of all those things added together. So 25 plus 4 plus 1, so that's root 30. And therefore, the unit vector in the opposite direction of u is 1 over root 30, negative 2 over root 30, and negative 5 over root 30. Okay, bring that back. We'll do d over here. U plus v dot u minus v. So first of all, what is u plus v? So that's negative 1 plus 3, which is 2. 2 plus 4, which is 6. And 5 minus 6, which is negative 1. Dot u minus v. So negative 1 minus 3, which is negative 4. 2 minus 4 is negative 2. And 5 minus negative 6 should give me 11. Dot product is multiplying the same components and adding. So x's with x's, y's with y's, z's with z's, and adding them all together. And it should give me a scalar. So negative 31. Next question, two vectors are orthogonal to both u and w. The only reason why this one might be tricky is if somebody didn't really know what that meant. What it's asking you to do is take the cross product. Because to get a product that's orthogonal to two vectors, that's what the cross product does. So u and w. So on the top I'm going to do u, starting with the y, and then the z, and then the x, and then the y again. And then of w, the y, the z, the x, and the y again. Okay, and so u cross w is 2 times 1 minus 0 times 5. So that's 2. 5 times negative 7. So negative 35 minus negative 1 is negative 34. And negative 1 times 0, that's gone. So minus negative 7 times 2, so minus negative 14, so positive 14. So that's one vector. So can I come up with another one? Well, it's just going to be a scalar multiple of that. I could take the opposite of that. I could do all kinds of things. So how about negative 1, positive 17, and negative 7. So I did the opposite, and I scalar multiplied it by half, just because it looked like it reduced nicely. Okay. And our final unit that we just finished, solve the following systems. There are two systems. Now, if you can't even identify what kind of systems they are, that's going to be really hard for you to solve. So hopefully you can do that. And this one is a line and a line. And I know it's a line because it only has one direction vector, and a plane has to have two direction vectors. They both only have one. So we're going to start by looking at the direction vectors. And they kind of look like there's something going on here, but there isn't. They're not scalar multiples of each other. So they are not parallel. So now what I want to do is get the x components, the y components, and the z components, come up with different equations, solve one of the systems, and check it in the third. Okay, if they are not parallel, they're not parallel in the stink, and they're not coincident. They're not parallel and coinciding. So they are either going to cross at a point or they're going to be skewed. Those are the only two options. So we're going to see which one of those two it is. So the x is, starting over here, 5 plus 6s equals 2 plus 1t. And the y's looks like negative 4 plus 4s equals negative 3 plus 2t. And the z looks like 1 minus 2s and 4 minus 3t. Six s minus t equals 2 minus 5 is negative 3. Call that equation 1. Equation 2 is going to come from the y's in this case, so that's 4s minus 2t equals 1. So that came from y. I simplified y. And then I am going to do I'm going to do 2 times 1 minus 2. So I'm going to multiply equation 1 by 2 and subtract equation 2. So I'm going to eliminate the t's, in other words. So that's going to be 12s minus 4s, which is 8s, negative 2t minus negative 2t, so that's 0. And negative 6 minus 1 is negative 7, so s is negative 7 over 8. And then sub that into equation 1. So 6 times negative 7 over 8 minus t equals negative 3. So I get negative 42 over 8 plus 3 equals t, and t works out to negative 9 over 4. And then I'm going to check, s equals negative 7 over 8, and t equals negative 9 over 4 in the z. So there, we're going to do it right here. Left side equals 1 minus 2s. Right side equals 4 minus 3t. And this works out to 11 over 4. And this one works out to 43 over 4. So what does that mean? Left side does not equal right side. Therefore, no solution lines are skew. All right, one more to go here. And take a look at this. This is a line in a plane, and I know that because there is no scalar equation of a line in 3 space, and this is 3 space because there's x, y, and z. And again, that's the first thing that you have to be able to do is recognize the different kinds of equations of lines and planes and really be able to do that easily. Otherwise, it makes it really hard. So I'm going to rearrange the equation of the line into parametric form. So the x equals negative 1 because it's negative 1 plus 0t. y equals 2 minus 4t, and z equals 0 plus 5t, so 5t. And then how do you solve this? Remember, you just plug those components, the x, y, and z components in parametric form, into the equation of the plane. It's super easy. So that's 3 times negative 1 minus 4y, which is 2 minus 4t, plus z, which is 5t, equals 10. And just solve. So I end up with 21t equals 21. How do you like that? T equals 1. And then I can interpret that. I'm going to get 0t equals 0, 0t equals some number, or t equals a number once I'm finished. And if I get t equals a number, then my interpretation is I can use that to actually find the x, y, and z components. So x is negative 1, y is 2 minus 4 times t. So that's negative 2, 2 minus 4. And z is 5 times 1, which is just 5. Therefore, the line and plane cross, and there's one solution, and it is at negative 1, negative 2, and 5. And that is that. That is our exam review, the in-class portion. I hope that all makes sense. And good luck.